The ocean covers more than 70% of our planet, yet we've explored less of it than the surface of the moon. Beneath the waves lies a world of darkness, pressure, and mystery. A place where sunlight disappears, strange creatures glow in the abyss, and entire ecosystems exist beyond human reach. Despite centuries of exploration and cutting-edge technology, the ocean remains one of Earth's greatest unsolved frontiers. Its depths challenge our science, its currents shape our climate, and its secrets continue to surprise even the world's leading researchers. Why is so much of the ocean still unexplained? What lies hidden in the deep? And how much of our own planet do we truly understand? Today, we dive into the mystery of the oceans, and the reasons we still can't fully explain them. The deep ocean presents profound environmental challenges that severely restrict exploration. Immense pressure is a significant hurdle, increasing by approximately 1 atmosphere for every 10 meters of descent. At the deepest known point, the Mariana Trench's Challenger Deep, the pressure reaches 1,086 bars, or about 15,750 pounds per square inch, psi, which is over 1,000 times the atmospheric pressure at sea level. This crushing force can deform or destroy robust materials, demanding specialized designs for submersibles and instruments. The deep sea is also defined by the absence of sunlight. Beyond approximately 1,000 meters, sunlight cannot penetrate, making these regions perpetually dark. Even in the twilight zone, between 200 and 1,000 meters, light intensity rapidly diminishes, with red and orange wavelengths being absorbed quickly, leaving only faint blue and green light. This darkness necessitates artificial illumination for visual observation. Traditional lights are often limited in range and can create glare from suspended particles, hindering clear imaging. Cold temperatures also define the deep ocean. Deep ocean water, which makes up about 90% of the ocean's volume, maintains a uniform temperature of around 0 to 3 degrees Celsius, 32 to 37 degrees Fahrenheit. Even near hydrothermal vents, where superheated fluids can reach 400 degrees Celsius, the warmth dissipates quickly into the surrounding frigid water. These low temperatures can affect the performance and reliability of electronic components and battery systems, adding complexity to equipment design and operation. Current deep-sea exploration technology faces constraints in overcoming these environmental extremes. Designing submersibles capable of withstanding the immense pressures of the deep ocean requires hulls made from strong, costly materials like titanium or specialized high-strength steel. These pressure hulls must maintain their structural integrity to protect internal systems and human occupants. Any weakness can lead to implosion. Only a few specialized submersibles can reach the deepest parts of the ocean, such as the Challenger Deep. One of the biggest challenges of ocean exploration comes down to physics. Dr. Jean Carl Feldman, an oceanographer at NASA's Goddard Space Flight Center, explains that the ocean, at great depths, is characterized by zero visibility, extremely cold temperatures, and crushing amounts of pressure. In some ways, it's a lot easier to send people into space than it is to send people to the bottom of the ocean, Feldman told Oceana. The intense pressures in the deep ocean make it an extremely difficult environment to explore. Although you don't notice it, the pressure of the air pushing down on your body at sea level is about 15 pounds per square inch. If you went up into space, above the Earth's atmosphere, the pressure would decrease to zero. However, if you went diving or hitched a ride in an underwater vehicle, those forces would start to stack up the further down you went. On a dive to the bottom of the Mariana Trench, which is nearly 7 miles deep, you're talking about over 1,000 times more pressure than at the surface, Feldman said. That's the equivalent of the weight of 50 jumbo jets pressing on your body. Effective lighting and imaging systems are difficult to develop for the darkness of the deep sea. Artificial light sources are essential, but water scatters and absorbs light, especially warmer colors, making it challenging to illuminate large areas or capture clear, high-resolution images. Suspended particles in the water can cause backscatter, creating a hazy effect, obscuring visibility and degrading image quality. Overcoming these optical challenges requires sophisticated camera technology and strategic light placement. Communication through vast amounts of water also presents a hurdle. Radio waves, commonly used for communication on land, do not propagate effectively underwater. Acoustic signals are used for underwater communication, but these are significantly slower than radio waves and suffer from limited bandwidth and range. Factors like temperature, salinity, pressure, and ambient noise levels can distort acoustic signals, leading to data loss or slow transmission rates, often measured in kilobits per second rather than megabits. The ocean contains more than 321 million cubic miles of water. To imagine that, think of something that's about a mile away from you. You might need to use a map app. Or ask a grown-up for a landmark. Now picture a giant 3D cube that same distance on each side. It's 1 mile long, 1 mile wide, and 1 mile deep. You would need 321 million of those to equal the ocean. Or think of a 1-gallon milk jug. All the water in the ocean would fill about 325 quintillion jugs. When scientists say we haven't explored much of the ocean, they don't mean just the bottom of the ocean. They mean all that water between the bottom and the surface, too. That's called the water column. It's the biggest habitat on the planet. The ocean contains more than 321 million cubic miles of water. To imagine that, think of something that's about a mile away from you. You might need to use a map app. Or ask a grown-up for a landmark. Now picture a giant 3D cube that same distance on each side. It's 1 mile long, 1 mile wide, and 1 mile deep. You would need 321 million of those to equal the ocean. Or think of a 1-gallon milk jug. All the water in the ocean would fill about 325 quintillion jugs. When scientists say we haven't explored much of the ocean, they don't mean just the bottom of the ocean. They mean all that water between the bottom and the surface, too. That's called the water column. It's the biggest habitat on the planet. Each deep-sea mission demands planning and coordination. Weather conditions can impact operations, as strong winds or high waves can make launching and recovering equipment unsafe, leading to canceled dives. Currents, both at the surface and at depth, also pose challenges, affecting the stability and maneuverability of vehicles. These realities and the resource allocation required limit the scope and frequency of deep-sea exploration. Unveiling the mysteries of the deep ocean is a monumental task, but one that holds immense potential for scientific discovery, technological innovation, and a deeper understanding of our planet. As we continue to develop new technologies and foster international collaboration, we can look forward to a future where the unexplored ocean is no longer a realm of mystery, but a vibrant and well-understood part of our world. Protecting this invaluable resource requires a concerted effort from scientists, policymakers, and individuals alike. By prioritizing sustainable practices, investing in research, and raising awareness about the importance of the ocean, we can ensure that future generations have the opportunity to explore and appreciate the wonders that lie beneath the waves. The ocean's secrets await, let's dive in responsibly.